Welcome to Ada University. My name is Quentin Oshem, and today I will walk you through the very basis of Ada statements. Let's get started. One particularity of the Ada language is that statements have to be written in a specific location in the code, which is a sequence of statements. It's typically open with the begin result word. So if you look at this example here, the second call to put line is fine. It is written in a sequence of statements after the begin keyword. However, the first put line is not. It's actually located in a declaration section. Writing this code will issue a compilation error. Ada provides the usual if statement, along with the else and the else if branches. You may notice that instead of using brackets, as in C++ or Java, we used full keywords to mark the end of the condition, and as a result, the parentheses around the condition are not required. One other aspect is the closing of the statement. Although it is optional in C, the end if is mandatory in Ada. The counterpart of the if statement is the if expression, which is very close to the ternary operator of C and Java. So an if expression is an expression that is evaluated depending on the result of a condition. The constraint is that all the branches of the condition are typed the same way. So here, in this example, I have a string as the result type of the expression, and the string is selected depending on the value of A or B. Ada provides the comparison operators that you would expect: equality, inequality, lower than, lower or equal, greater than, greater or equal. One interesting note here is that the equality is a simple equal, as opposed to double equal is in many other languages. This is allowed by the fact that the assignment is colon equal. The different operator is a little bit different as well. While it's exclamation mark equal in many languages, in Ada it is / equal. On the side of Boolean operators, you will find the usual OR and XOR operators, as well as two specific ones, which are OR else and AND, which are shortcuts operator. Which brings us to an important caveat. In Ada, the AND and the OR operator are not short circuit, which is highly counterintuitive if you're coming from other languages. That means that both operands will always be evaluated before returning the result. The short circuit operators are AND then and OR else, which will indeed evaluate the right-hand side only if necessary. In this regard, it is perfectly fine to have a coding standard that completely forbids the use of the simple AND and OR operators and enforces the usage of short circuit operators. Environments such as the GNET compilers have means to verify that indeed only those short circuit operators are used. The equivalent of a Java or C++ switch statement is a case statement. There are a couple of notable differences. The first one is that a sequence of statements within an alternative in Ada will systematically stop when reaching the next alternative. So, in other words, there is no need for the break instruction at the end of the sequence. Another interesting difference is that it is possible in Ada to use combination of ranges to define the value that will be used for a given alternative. So for example here, I could express the fact that digit should be displayed for all values going from -9 to -1, combined with all values going from 1 to 9. The equivalent of a case statement in the expression world is a case expression. It does the obvious thing, that is, selecting an expression based on the value of a condition. There are two important additional rules to understand with regards to case statements. The first one is the value defined in the various alternatives of the statement have to fully cover all the possible values of the expression. In this first example, v is of type integer, and I'm only providing an alternative for the 0 value. So I'm missing all of the other possible values for integer. Therefore, this will raise a compilation error. I could very easily fix this piece of code by adding a whenOther statement, encompassing automatically any value that has not been previously mentioned. The other rule is that for a given value, the branch, the alternative, should be unique. In other words, there cannot be any overlap amongst the various ranges. In this second example, as you can see, on the first alternative I'm taking 0, and on the second one I'm getting all values going from the first integer up until 0. So there is an overlap. For the value 0, I don't know if the first branch or the second branch should be taken. This will be analyzed and reported by the compiler and issue compilation error. One side effect of those two rules is the fact that the ranges within the alternatives need to be statically analyzable by the compiler. In particular, it will not be possible to have variables there. Loops are created through the loop and loop block. In the first example, I'm creating an infinite loop that will print hello on the screen and then wait for 1 second. This waiting for 1 second is implemented through the delay statement. As with many other languages, we have the while loop, which is going to loop up until a certain condition is met. In this second example, I am looping as long as a is below 10, and as long as this is the case, I will print hello on the screen and increment a. An infinite loop can be created through the loop and loop structure. In order to exit such a loop, the exit statement can be written. As you can see on these first two examples, there are two ways to write this statement, either unconditionally through exit, or providing a condition to be true before exiting the loop, which would be here the exit when option. In case of nested loop, it would be possible to provide names to loops and then say to the exit statement if we are expected to exit the inner loop and the outer loop. And that's the case in this last example, where I'm exiting loop 1 directly from within loop 2. The for loop in Ada is specifically designed to iterate over a range of values. There are some advanced ways for iterating over an abstract container, but we will not talk about this here. So in the first example here, I'm iterating over a range from 1 to 10. The step of the iteration is always equal to 1. And such a loop can only iterate over discrete values, so namely integers or enumerations. The range has to be given in incrementing numbers. Having a range from 10 to 0 will issue an empty range, and actually in this second example there will be no execution of the statement putLine hello. The correct way in Ada to write a loop that goes backward is to use the reverse keyword within the iteration definition and then provide the range in the incrementing order. A for loop automatically creates a variable that will hold the index and that can be used within the loop. This variable can be explicitly typed, as in the first example, saying for x in the type character from 1 to 10. It may be any kind of discrete type, and if I miss the range, then the whole range type will be taken. Here I'm saying for x in character in this second example, so I will iterate over all the possible values of the character type. One important point is that this index is constant from within the loop, so it is not possible to change the value of this index in the loop itself. Only the for loop can automatically increment that variable at each iteration. One last word about loops. The range in which the loop is going to iterate is only evaluated once, when entering the loop. Further changes to the expression that is doing this evaluation will not have any effect on the loop itself. So in this small example I have a loop going from A to B, and I'm incrementing B at each step. That will however terminate, because the B that is going to be incremented within the loop will have no effect over the range that has already been elaborated and computed. One additional information concerning declare blocks. We said earlier that declarations can only be written in declarative blocks, and statements can only be written in sequence of statements. But in some situation, after having written a couple of statements, it is useful to be able to create a local declaration which scope is smaller than the scope of the subprogram and which may rely on computation that has been made earlier. So Ada allows to create a local declaration block within a sequence of statements using a declare block. In this example, in particular, I am adding a declaration to a new variable. I'm doing some initialization to this variable, maybe some work later on, and then when I reach the end, that will be the end of the scope and the variable will be destroyed. One last word on statements. It is illegal in Ada to have a sequence of statements that is empty. In other words, everywhere where we accept to have statements, we should have at least one statement. But in a number of situations, it's perfectly fine to have an empty sequence of statements. Maybe the only thing that we want to do is declaration, and we want the benefits from the side effects of the declaration. Or maybe the code is not written yet, and we know what we're doing, and we just need to tell to the compiler this is an empty place, and it is expected to be empty. This is done using the null statement, which will be one statement that does nothing. Let's now verify your understanding through a quiz section. For all these quiz sessions, if you find no error in the code, click on the green box next to the yes, and then submit. If you do find errors, click on the errors in the code, and then hit submit. This is not correct. In Ada, the operator for equality is a single equal sign. Assignment is not an operator in Ada, so it cannot be used in an expression, yet alone a condition. This is a compilation error. All the values that can be taken by an expression within a case statement have to be covered by the various alternatives. In here, I'm looking at a from 1 to 9, from 10 to the last integer, from the first integer to -1, and I forgot the value 0. This is a compilation error. Within the choices of a case statement, all value should be unique. In this case, I have a clear overlap between the first and second alternative. And if I get a value like 2, for example, I do not know if I should be taking the first one or the second one. There are duplicates which are generating a compilation error. Since I'm going to enumerate the values of the expression and verify that they are completely covered, I need to use a discrete type in the expression that is either integer or enumeration. Here I'm writing a case statement on a floating point value. This is incorrect and will lead to a compilation error. So to implement this behavior here, I would have to write a regular if statement. The index of a loop is a constant within the loop. It cannot be modified. So this is a compilation error because I'm trying to assign a value 10 to I within the loop. Remember that the value for a range have to be given in incrementing order. Here, 10 to 0 is decrementing. So in Ada semantics, that means empty range. There is no statement from within the loop that will be executed here. The correct way to writing this loop, if I want to go from 10 to 0, is to say for I in reverse 0 to 10. This is incorrect. I'm using a Java or C++ notation here by writing exclamation mark equal for inequality. In Ada, this symbol is /equal. This is an interesting case. From the Ada semantics, that's perfectly correct. There is an I that is declared outside of the loop, which is a variable of type natural, and then within the loop I am declaring a new I that will be used for the indexes. However, although this is perfectly fine, this may raise misunderstanding, since there are two I's here and the developer might mean that he wants to be able to modify this I variable from within the loop. So this is discouraged. The range over which a loop is iterating is computed only once when entering the loop. At this time, x equals 1, so the loop is going to iterate from 1 to 1. The fact that I'm modifying x within the loop doesn't have any impact in the loop iteration that has been computed before. So this loop will indeed only loop once, and only print A on the screen once. This concludes this lesson on Ada basic statements. Stay tuned, there is much more to come.